Hello everyone and welcome to the follow-on video. Okay, in the previous video of Newton's laws we looked at force. Alright, in this video we're going to be looking at calculating the different frictional forces such as the static frictional force and as well as the kinetic frictional force. Alright, so what we're going to do here, okay, first of all, we're going to uncover the formula for calculating maximum static friction. Alright, that formula is calculated by F, alright, S max, so the maximum static friction, Fx max, okay, is equal to mu s, which is the coefficient of static friction, times the normal force. Alright, and we're going to have a look at a worked example quickly. So this is a worked example that is out of the Sciavula grade 11 textbook. Alright, so question 1. Okay, we're just going to have a look at 1. Alright, so the question, let's read it together. A box resting on a surface experiences a normal force of magnitude 30 newtons, and the coefficient of static friction between the surface and the box, mu s, is 0.34. What is the maximum static frictional force? Alright, now the solution, as the Sciavula textbook has given us. Step 1, we first denote the maximum static friction. So we know the relationship between the maximum static friction, Fs max, alright, the coefficient of static friction, mu s, and the normal force to be given by the formula. Fs max is equal to mu s times n. We have been given that mu s in the question is 0.34, and the normal force is given by 30 newtons. Okay, this is all the information we need to work out the calculation or work out, okay, what is the maximum static friction. Okay, so we've been given what we need, we have written it down, so we know what is required of us. We simply plug it into the formula, so Fs max is equal to 0.34 times 30, and that gives us an answer of 10.2 newtons. That is the maximum magnitude of static friction. Alright, hope everyone understands. Okay, that's a very simple example. Okay, in the next video I will be doing an exercise which will deal with calculating more intricate questions using maximum static friction, but for now that is just the basics for calculating maximum static friction. Now we know how to calculate maximum static friction. Now let's have a look at how do we calculate the kinetic friction. Now the formula is very similar from the static friction formula. Only thing we do now is replace the s with k. So the formula for calculating maximum kinetic friction is Fk is equal to mu k times the normal force. Now, the kinetic friction, this is where the object is moving, but it still experiences a frictional force. Okay? Although the object is moving, friction is still acting on the object. Okay, so let's go have a look here quickly at a worked example where we need to calculate the kinetic friction. Alright, so this is a more intricate question. This question is a little bit bigger, more information. Okay, so let's read it together. The normal force exerted on a pram is 100 newtons. Okay, so what I'm going to do, I think I'll work this on the whiteboard a little bit with you. Okay, so in the right hand corner I'm going to write down the normal force is equal to 100 newtons. Perfect. The pram's brakes are locked so that the wheels cannot turn. The owner tries to push the pram, but it doesn't move. The owner pushes harder and harder until it suddenly starts to move when the applied force is 3/4 of the normal force. Okay, we can put that there. So we denote force applied. All right, F, app. All right, force applied. They tell us that it's 3/4 of the normal force. Okay, 3/4 of the normal force, and we know the normal force is 100 newtons. After that, the owner is able to keep it moving with a force that is half of the force at which it started moving. Therefore, what is the magnitude of the applied force at which it starts moving, and what are the coefficients of the static and kinetic friction? All right, well, as the solution suggests, the first step is maximum static friction. All right, so in the question, they tell us the owner of the pram increases the force he is applying until the pram starts to move. This will be equal to the maximum static friction, which is given by the formula Fs max is equal to mu s times the normal force. Okay, because the pram is static and he applies a force to it until it starts to move. But until then, until it moves, the pram is still stationary. Now, we are given that the magnitude of the applied force is 3/4 that of the normal force. So as the solution suggests, and I think I'll rewrite it here, all right, that the force applied, so we can look at that. The force applied is equal to 3/4 of the normal force, so 3/4 of 100, right? And we know the 3/4 of 100 is 75 newtons. This is equal to Fs max. Okay, just like in the suggest. Okay, Fs max, okay, is equal to 75 newtons. All right. We are given that the magnitude of the applied force is 3/4 of the normal force, so hence, that means that Fs max, or the maximum static friction, is equal to 75 newtons. Step 2. Now we need to calculate the coefficient of static friction. We already know what is the frictional force, all right, or the static frictional force is 75 newtons. So we can just plug that into our formula because we already know the normal force, and we can calculate that the coefficient of static friction is equal to 0.75, sorry. That is the coefficient of the static friction. Now that we have the coefficient of the static friction, we can now calculate the coefficient of the kinetic friction. Now, the magnitude of the force required to keep the pram moving is half of the magnitude of the force required to get it to start moving. So we can determine it from Fk is equal to half that of Fs max. So we know Fs maximum was 75 newtons, so half of that is 37.5 newtons. That is the magnitude of the force required to keep the pram moving. All right, we know the force that it took to get the pram to start moving, that was 75, and the force to keep it moving is half of the force that it was needed to get it to start moving. All right, so we now know what the frictional force or kinetic frictional force is equal to. That's equal to 37.5 newtons. Now we know the relationship between the magnitude of the kinetic friction, magnitude of the normal force, and coefficient of kinetic friction. And we can use it to solve for the coefficient of kinetic friction. All right, so Fk is equal to mu k times n. We know what Fk is equal to. We just worked it out in the previous on the previous slide. All right, in the question, 37.5 is equal to mu k times 100 newtons. All right, and mu k, or the coefficient of kinetic friction, is 0.375. Okay, quite simple. Not very intricate at all. All right, a lot of work that we needed to do to get to the coefficient of kinetic friction. Okay, but if we know what we're working with and we write out what we have been given, it's very simple to find the answer. Alright. Now I want to explain the force of tension before we move on. Alright, now the force of tension, alright, tension is the magnitude of the force that exists in objects like ropes, chains, and struts that are providing supports. If I have a block over here, alright, let's say I have a block here attached to another block by a rope. Okay, and I am alright, and all of a sudden over here there's what we call a pulley system. Alright, and there's another block over here. So now this block, which is the heaviest block, let's say this is 100 kilograms. Okay, this is only 75 kilograms. And then this block here is only, let's make this 50. In this rope, that rope, and that rope, or that part of the rope, there is the force of tension. Okay? There's the force of tension that exists there, providing support. Okay, so here, okay, the block is the pulley system. The 100 block is obviously the force of gravity is pulling it down. Okay, and the rope is trying to hold on to the block at the same time, trying to hold on to this block, and at the same time trying to hold on to that block. All right, otherwise the rope will snap. All right, so that is force of tension. So for example, just besides the example that I have explained here in the whiteboard, the examples also are tension forces in the ropes that support a child's swing hanging from a tree. So a swing hanging from a tree, there is force of tension in the rope, okay, which is holding the swing, and the rope holding itself to the tree as well. It's supporting. Okay, so it's almost like it's fighting the force of gravity to stay there. Otherwise, if it was too heavy, if the mass was too heavy, and the force, that means the mass would outweigh the force of tension, alright, and then the rope will snap. Okay, so there's tension and everything. So if another example would be a tug of war. Alright, tug of war, where we have a tug of war battle where a group of people pulling another group of people in by a rope. There is tension in that very big rope. Actually, there is tension, although it is maybe not as big, but there is tension there. Okay, which is kind of holding the rope together so that the rope does not snap and we don't fall all the way back and possibly injure ourselves. Okay, so stay tuned for some more information regarding Newton's laws, alright, in the next few videos. In the next video, we will be looking at how to draw force diagrams.